Hi, I'm Mr. V, and today we're talking about illustrative math, solid geometry, lesson 2, slicing solids. And by the end of the lesson, the goal is for you to be able to say, I can identify a three-dimensional shape that generates a certain set of cross-sections. And number 2 is I can visualize the cross-sections of a three-dimensional shape. And to start this off, we had a bell work problem where you were to take this cylinder and to slice it. And what did the cross sections of the cylinder look like? The second part of this was to look at the cube, and when we slice it, what do we get? So I'm going to make my video bigger here so that you can actually see me, and maybe turn on the light a little bit. So I have here a cylinder, and if I were to slice this horizontally, you can see that it would be a circle. It would be a circle if I did this. And if I were to slice it straight up and down, I might, let's see if I can do this. It could be like this. So you can see I can slice it straight up and down. And when I do that, my cross section, this piece that is cross section is a rectangle. It's going to be a bit rectangular like that. That's what I'm looking for. It's going to be a two-dimensional object. If I were to slice this at a slant, here's my slant. You can see how when I do this from this end, it looks like a circle, but if you look at it, I'm slicing it at a slant, and really what it is an ellipse. We don't call this an oval; we call this an ellipse. Let me see if I can get it out of here. You can see here's what it looks like: an ellipse. If I were to cut it at a partial ellipse, so it doesn't go all the way across, maybe it hits the midpoint or somewhere across the middle of here, I can do this. I'll do this with some salt. I'm using salt here, not sugar. Don't want to spill sugar. You can see how this would be like this kind of shape. So it'd be not. This is not an oval. You could call it an oval, but it's really it's an ellipse. And this is not a parabola, but it's a parabola. It's a conic section, but it would be like a part of an ellipse. And so if I were doing this on the Desmos, I would draw it like, let me see what I would draw it like. I have a couple of figures here that you could draw. One would be the circle. I could have a rectangle. Maybe it's a very tiny rectangle like this, thin rectangle. If the width is the same as the diameter is the same as the height, I could have a square. When I do it going from the top corner all the way down to the edge, it's not going to be it could be like this from the top corner to the bottom. This would have two foci as opposed to one like a circle does. And then if I only did part of it so that like it intersected just the top part or just the bottom part, it might be something like this. It's not going to be a triangle. You cannot get a triangle out of this. There's no way to make a triangle out of this. It would be a part of an ellipse, something like that. Now the cube is even more fun and more interesting. And when we do it, of course, you could do it slantwise. And I'll do this once again big with my video here so you can see my picture nice and big. Here's my cube. And if I did it across the top, I have this type of figure. And if I could slice this at any level, so this would be a cube. Here's a cube. I could do it up and down. Or maybe I do it in the middle, or maybe I do it over to the side, something like that. So do it towards the side. You can see this would be a rectangle. I can also do it from the corner, and I can do it directly from the corner where it goes up to one of the sides. You can see how this actually makes it to the sides. This would be a triangle. Maybe you get an equilateral triangle. I think you could do it with a right triangle if the right angle is up here at the top. Right triangle. It could be a scalene triangle. So all kind of triangles that you could do this. Here you can see I've got, for this one, I've got this distance is shorter than this distance, but you can see the triangle. And when I hold it up, you got the one distance is shorter than this one here. So this is a scalene triangle. A lot of different things. Then I'm going to put my salt in here. When I do this, of course, I've got the triangles. If I go a little bit further than the triangle, so I go up like this, here I've got Superman. I've got a pentagon. Maybe you can get a regular pentagon out of it, but I've got a pentagon. And if you go all the way up to the top, where you're using all 6 faces, you could actually make a hexagon. And so we tried this. We worked on this a little bit. Then we went to this page, and we went in this Geogebra link. I'm going to show you and demonstrate it for you. In this link, make myself small again here. We have 2 pictures. We have the one is a picture of a cube, and I can grab a hold of this and twist it, turn it. You can see there's a plane that's slicing this. And when it slices it, I get this figure. This is this cross section. This is the 2-dimensional cross section that you get from slicing the 3-dimensional figure. And these dots here, 3 dimensions, three points determine a plane. So I can move this up or down. And when I do, look, there's a pentagon, goes down to a quadrilateral, which is a trapezoid. The opposite sides are parallel. And then it goes to a triangle, and it goes even further. And I can move this thing left or right by clicking on it. I can move it over this way and make it into a trapezoid again. Notice the top and the bottom are parallel. So, and you can move these other points as well, but I just moved the 3 to try to show you that to change the plane around. And we played around with this a bit today. That's what we did for a big part of the class. Next thing was to look at these pictures. These are cross sections of a single figure, and they're all sliced in the same plane. So they're parallel planes. And you could say, well, this is a triangle. Yes, but that's not the 3-dimensional figure. The 3-dimensional figure is what results when you stack these all together. And we're stacking them in places that are parallel. What kind of figure would this be? And I've got a figure over here that shows it. So not this one. Okay, I'm going to do it right here. Can you see there's going to be a pyramid? It all comes to a point, and it has a triangular base. So we would call this a triangular pyramid. If it went straight up, we would call it a right triangular pyramid, but we're going to just call this a triangular pyramid. We also call this a hedron, Hedron. Like you've heard of a polygon, a trigon, a quadrigon, a hexagon, a heptagon, a cosagon. Those are 2-dimensional figures. When it's a hedron, that's a 3-dimensional figure with polygonal faces, polygons for faces. They call these parts faces, and these are edges, and these are vertices. This would be a tetrahedron. Tetra is from the, not tetra, tetra. I keep messing that up. Tetra. Tetra is 4. 1, 2, 3, 4. And I've got a model one of these right here. Let me see if I can make this nice and big for you so you can see it. So here's a tetragon, or a triangular pyramid. All comes to a point. A pyramid has a base that's a polygon. Like this would be a square pyramid, and they all come to a point. All the faces are triangles. These are faces. We don't call them sides, we call them faces, and that's to not mix up the edges. So when you're talking 3 dimensions, you have edges, faces, and vertices. Now, if you watch this for a second, and I fill a little bit of it, see how this is a triangle? There's a triangle. I make it, put a little bit more. There's another triangle, and a little bit more. There's another triangle. And they all come to a point, and these would be like dilated pyramids. They're all the same shape. They all come up to the point, which is the vertex. Now, the second one that we looked at on this set of, here, was these circles. Someone tried to pass this off as a cylinder, but I'm thinking the cylinder is going to have all the same size circles. These are all different. And if you think about it, in this particular drawing, here I have a very small circle up at the top, and then you go down a little bit further and you have a different size circle. So I'll do this in a different color. Different size circle right here. And it goes around at the backside. It comes around. That would be a circle. If you looked at just the cross section, you sliced it, and then you could get another circle down further down. And these are all bigger and bigger, bigger and bigger and bigger circles. Try to do it in a different color. Didn't do it in a different color. But you can see that these would all be flat. The way that we draw this sphere is we make a circle, but then we draw this ring around it. This is like one of the cross sections. And if you were to draw this cross section, this area here would be a circle. Like that. Okay. This last one that we looked at was one that I mentioned before. Notice it's got triangles, it's got a pentagon, it's got a hexagon, and this would be your cube. So if you wanted to do the more part of this, you could. But notice here, if I stack these triangles, I get a triangular pyramid. I get my sphere, and this is our cube. I don't know if you can see it very well, but this is our cube. And it's got all kinds of different shapes that are created from it, cross-section areas. When is this used in real life? Well, maybe you've heard of tomography, computer tomography, CAT scans or CT scans. A traditional X-ray is just of the lung. A CAT scan takes a cross-sectional area, so the doctors can look at all the different organs and parts and inside, even in your brain. There's this large machine. They put you on a bed and they set you through it a little bit at a time. And as you go through it, the X-ray source will take a scan. They used to do this from a single point. Now they do it. This X-ray actually goes all the way around. It makes travels all the way around while you're doing it. So it's pretty cool. I think that's what happens. I'm not sure. I think it says here, scanning as well as the spiral scanning is what they call it. Spiral scanning. So they're detectors all around. Anyway, this is a real-world application of using cross-sectional areas. You should read the summary on the lesson. And then the last thing is this pyramid. And this, folks, is a test question. So here you have this pyramid. What shape would the cross-section be if you cut a horizontal plane? What would it be if you did a vertical plane going through the top point of the pyramid? And what would it be if you did a diagonal? So I'm going to show you a few of these. Looking at my picture here. If we were to cut across horizontally, it's going to go this way, it's going to keep going horizontally, and this would be a square. If I did it a little bit higher, maybe up here somewhere, here, you have this and this, and even higher still. You can see that each one of these cross sections is going to be a rectangle, or a square, excuse me, because it's a square pyramid, so this would be a square. If I were to go from the vertex up here and cut, and let's say that you went all the way from this side over here to this side down here. If I do that, this would be a triangle. This shape here would be a triangle. If I cut from the vertex and I went way over here somewhere maybe, and then over to this longer side, this would still be a pyramid. Even if I brought it out or brought it in, it would still be a triangle, excuse me, not a pyramid, triangle. The last piece, though, this is interesting, and this is the end of our bell work before I stop the video. And I want to show you this with my model again. Here I have a square pyramid. You define it by the base. The base could be a polygon of any kind. All of the sides are triangles, come up to a point. And if I were to put my salt mixture in here and try to make this into a shape, can you see that this could be a kite? Could be a kite. It could be a trapezium. Notice a trapezium is not a parallelogram. Excuse me. It's where all of the sides are different. Oh man, I just made a mess. None of the sides are parallel. A trapezium is like a trapezoid, has one pair of parallel sides. Trapezium has no pair of parallel sides, and that would be a trapezium. And could be a triangle. There could be other things it could be. So anyway, that's what I've got for you for today. Good luck and success.